Okay, good morning, everyone. I think we can start the seminar. So first, see some opening remarks. Super welcome to the 15th Open Seminar in Frontier of Nuclear Physics. This seminar series is organized by the Institute of Modern Physics, the Key Lab of Nuclear Physics and Ion Application, Fudan University, and the Shanghai Research Center for Theoretical Nuclear Physics, SFC. And it's also supported by the program of introducing talents of discipline to universities, the Journal of Nuclear Science and Techniques, and it's live streamed on coshare.com. So today it's our great pleasure to welcome the speaker, Professor Marco van Leeuwen, who is the ALICE spokesperson. And I'm very happy to let you know that today, this week, Marco is visiting China now, stopped by each ALICE institute in China. So it's here. Okay, so let me very briefly introduce Marco. So he now is a senior scientist at Nikhef Amsterdam and is a guesting professor at CERN, Geneva. So his research focuses on the strong interaction and the formation of the quark-Gluon plasma in high-energy collisions. He completed his PhD at Utrecht University in Netherlands on the measurement of kaon production and search for open charm in high-energy collisions with Na49 experiment at CERN. As a postdoc at Berkeley lab, he worked on high PT in jet physics and determining property of the QGP with a hard probe. Then since 2007, he moved back to Netherlands and then work on those QGP related things, then joined the ALICE. So now, as I mentioned, he is the current ALICE spokesperson. So today he will show us some, as you can see already, the screen is shared, so you can see the title. So now we welcome Marco.
Okay, thank you, and thanks for having me. I'm happy to be in China and present our work with the ALICE collaboration. This is awfully wanted, but it may be okay. Yeah. And so I'll present a mix of some recent results and a bit of the future plans of the collaboration, and the current status of our data taking of the new Run 3. And yeah, it's hard to choose topics, so I try to be a little bit selective. And then if you have questions after the talk, I'll be happy to answer them. Also, if during the talk something isn't clear or so, feel free to interrupt me. So just as a bit of introduction, I wanted to kind of place our field in the larger area of physics. So I skip a little bit the introduction about the strong interaction because I think most of you might be familiar with that. But I think one thing is nice to think about is that if you want to study particles and interactions, there are different regimes or different types of study that you can do. And what is for accelerator people the most common is to think of the interactions between free particles, which you study with two-body scatterings, well, for example, by colliding beams. Like E+E- collisions that have been done at lab, and also proton-proton
recording in progress,
the LHC. And this works both for the electromagnetic interaction and for the strong interaction. Now, if you think of another regime of the interaction of bound states, which are normally few-body interactions, then in electromagnetism, you have the whole field of atomic physics, where you look at energy levels, excitations, and so on. And at the strong interaction, the analogous field is what we call hadronic and nuclear physics. And I'll show a few examples of how we actually use ALICE data or the heavy ion collisions as a laboratory for hadronic physics later on. So this is where you have bound states of quarks that are bound by the strong interaction mediated by gluons. And the field the part that is most prominent for us is the many-body physics of QCD. So in electromagnetism, many-body physics means condensed matter physics, where you have things like thermal and electrical properties and superconductivity and many other intricate phenomena. And in QCD, you have a similar set of phenomena. Now, the main state of many-body, the main many-body state that we can study in in QCD is the quark-Gluon plasma, is the high temperature state. And this is the goal of heavy ion physics, is to study the condensed matter physics of QCD, where the constituents are really the fundamental particles, the quarks and the gluons of QCD. Now, and as you know, the main topic then is the phase transition of the QCD and the high temperature phase. So this is just to remind you of how that works. So here you see a theory calculation using lattice QCD of the energy density divided by the temperature to the fourth as a function of temperature. And you see that at low temperature, this energy density is relatively small. This is where quarks and gluons are confined in protons and neutrons, which can be bound in a nucleus, or they can form a gas at higher temperatures. And then as you increase the temperature at the critical temperature of about 155 MeV, there's a very large increase of the energy density over the temperature to the fourth, which means that there's a large increase in the number of degrees of freedom. And that is because there's a phase transition to this deconfined quark-Gluon plasma phase, where now the number of degrees of freedom is the number of quarks and gluons, which is about 40, if you count the spin degrees of freedom, instead of just the 3 pions. And this phase transition happens at about 155 MeV, which is 10 to the 12 Kelvin, and at LHC we routinely go above that, and we study actually the high energy phase of QCD. Now, just to remind you of the Alice experiment, so what I will show you are all results from at least from the LHC. So LHC is the largest particle collider in the world. It is near Geneva, at the border between France and Switzerland. This is an aerial picture of the area. So you see the airport, you see the LHC, which is drawn in, so it's underground. So in the landscape, you almost don't see it. It's a ring of 27 kilometers, and we have proton-proton collisions at about 14 TeV and lead-lead collisions at a bit more than 5 TeV per nucleon pair. And ALICE is one of the 4 large experiments at the LHC. Is located here in a small town called Saint-Genis. And this is a picture of when we were installing parts of ALICE inside the big magnet. So the orange thing is a big electromagnet which we use to measure the magnetic fields, to measure the momenta in the magnetic field. And then you see this clear structure of, detector systems that sit around the beam pipe. So the beam pipe is here in the middle, and the blue thing here is the end plate of the time projection chamber, which is the main tracking device. But inside it is the inner tracking system, which we just upgraded. So we just upgraded the Alice detector in the last long shutdown. So 2019 to 2021, we installed these new detectors. And I wanted to highlight a few of them because they really improve the performance of the detector. So you have here on the left, you have the ITS and the MFT, the muon forward tracker, which are silicon pixel tracking devices. We have 7 layers. What you see here in the photograph are only the outer 2 or the outer 4 layers. The inner 3 are inserted inside and not yet installed in this picture. So this is about 12 billion pixels of 30 by 30 micron. We also installed these new fast interaction trigger detectors, which are a big scintillator detector and Cherenkov counters to give fast signals to trigger some of the detectors for to signal the interactions. These sit at forward and backward rapidity. And then the other big upgrade is that in this time projection chamber, we changed the readout chambers. We changed them to this gas electron multiplication foil readout, which has the same gain as a multivariate proportional chamber or similar gain, but it has less what you call ion backflow. So the charge drifts through these foils and is amplified. And in a classical multivariate proportional chamber, quite a bit of charge leaks out back into the TPC, which limits the readout rate that you can have in the TPC. And with this upgrade, we can now read out the TPC continuously. So it's basically always on, and you're continuously collecting the data. And this allows us to collect, for example, lead-lead collisions at about 50 kilohertz, which is about 50 times more than we had in the previous round. So this is really an enormous upgrade. And in addition, the pointing resolution has improved with the ITS. And to process all this data, we now have a big online farm that processes it as a first processing step that reduces the data output of the detector. And I just want to briefly show you the most recent news on our running and data collection. So we have now been taking data with proton-proton collisions for 2 years in 22 and 23 for a total of 29 inverse picobarn. And these were all first recorded to disk. And then we have a data reduction strategy, which we call an asynchronous trigger, which is kind of a high-level trigger that, however, runs, let's say, offline. So we collected all the data on disk. This is 10 to the 12 events. And then we run reconstruction and a trigger algorithm that selects certain events. And then what we call skim the data. We only select the raw events that are selected by these triggers. The selectivity of the trigger is about 1 in 10 to the 4, and we have a whole menu you see here on the bottom right. You don't need to read everything here, but there's a large number of different trigger selections, things like high multiplicity, multi-strange baryons, low momentum difference triplets for femtoscopy, nuclei triggers, and Fos-NEM-Cal, so electromagnetic calorimeter triggers. And then, since we have this continuous readout and you have a long drift time in the TPC, we always keep a time interval around each triggered event, which also then contains quite a large sample of minimum bias events. So this selection has been performed, and we now have first results from this PP data. So I just wanted to show you a few performance plots. So here on the left, you see the impact parameter resolution from the data from round 3 and the Monte Carlo simulations. So you see that we are getting close to the expectation. We are already better than we were in round 2. There's still some calibration and alignment to do to bring it the last little bit. And with the good pointing resolution, we can select all kinds of heavy flavor signals. And with the 1 billion or 1 trillion events that we have, 10 to the 12, we get very, very high statistics for all these mass peaks. And even more exotic decays we can reconstruct, like this Xi-C. And then many of the other detectors, like the Fos-NEM-Cal, also work as expected, and we have very nice by zero peaks and jet energy measurements. Now I want to show one preliminary result from the round 3 results, from the round 3 data. So this is the measurement of the Psi2S and the J-Psi at mid rapidity, with a decay to electron-positron pairs. Also here you see a very high statistics measurement. So this big peak is the J-Psi, which we had already measured. But now the small peak here is the Psi2S, is the excited state. And here on the middle, you see then the main result. So this is the Psi2S to J-Psi ratio as a function of transverse momentum. And you see here the new measurement in red at mid rapidity compared to the measurement at forward rapidity with the muon arm. And then the blue points are the previous measurement from round 2. So you see that the upgrade really delivers a very large increase in statistics. And we can now measure this down to 0 PT at mid rapidity. It's the first measurement down to 0 PT at the LHC. And here you see a comparison of this Psi2S to J-Psi compared to world data. And you see that the precision already now is very competitive with previous measurements. But the value is in line with what people have seen before. Now, still staying with the data taking, the main update, the recent update is that we now also took heavy ion data. This is very fresh. So the heavy ion run started about a month ago at 8 p.m. or around 8 p.m. on Tuesday, 26 September. You see here a picture of the control room with the crew of people who were present right at the start of the heavy ion run. So this was the first time that we took high-rate heavy ion data. So there were many detector experts around to make sure that we could get going very effectively. And that worked very well. At the time, we started out with lower rate, but soon it ramped up to about 50 kilohertz interaction rate, which means that that's why I show you this display here. that we get an input rate into the high-level trigger of about 600 to 800 gigabytes per second, and then the output to the storage system is about 200 gigabytes per second. So very high data rate, but this all worked flawlessly. And this here on the right, you see the collected luminosity. The heavy ion run actually ended yesterday morning at 4 a.m. Geneva time. And we collected 1.5 inverse nanobarn of heavy ion data, which is about 11.5 billion events, which will be all kept. So with heavy ion collisions, we just keep all the data and we run the reconstruction. We can run the reconstruction several times to improve the performance. So this is very fresh. I don't have any heavy ion results, but I thought it's good to show that this run was working very smoothly. Now and then let's go a little bit to the physics. So this is a event display from heavy ion collision. I just wanted to show you how impressive these events look like. So you have here the detector with the time projection chamber again in blue, and then the inner tracking system, and all these white lines are tracks that are reconstructed. So this is from an event from early during the run this year. And then, of course, what we do is we measure the momentum and we identify particles, and we do correlation measurements to expect or to determine properties of the plasma and things like hadronization mechanisms and so on. Before diving into the results, I just wanted to show you this animation. I think it's very illustrative to show how we picture a heavy ion collision. So this is the initial state when the ions collide, and you see this is a model calculation where now we have a fluid expansion, and then as it cools down, you see that that there's hadronization, and the white spheres are then the hadrons that are produced in the collision. So sometimes we like to call this little bangs, where we produce the Quark-Gluon plasma, the primordial liquid, in the laboratory, and we can study it. The other aspect that I think is always important to remember is that in a heavy ion collision, you do not only have this Quark-Gluon plasma that you want to study, but you have initial state dynamics and final state dynamics that you have to somehow unfold to make sure that you understand the whole process. So then I will go through a few results starting from the initial state. So these are a few results on ultra-peripheral collisions, for which we had a number of recent results, and we had this article at the CERN homepage, which has this very nice sketch. Ultra-peripheral collisions are collisions where the nuclei do not really hit each other, but in fact, one of the nuclei emits a high-energy photon that strikes the other nucleus, and it probes the structure of the nucleus. So that is why this is really an initial state measurement. You probe the structure of the nucleus with a high-energy photon beam that is generated by the nuclei. You can also use these in proton-lead collision, or in lead-proton collisions, I should maybe say, to probe the structure of the proton. And then depending on the wavelength of the photon, which you can measure by looking at the rapidity of the final state, you probe either long wavelength or short wavelengths in the nucleus. And here you see one of our recent results. So this is the production of JPSI, coherent JPSI production in these UPC collisions. It's a function of rapidity. On the left is the cross-section measurement. On the right is then the interpretation in terms of gamma lead cross-section. So more going close to this analysis of the internal structure. And what you see here is that the comparison to several models where the impulse approximation and starlight are models that do not have nuclear modification. And you see that the data actually sit below this. So they show that there is a gluon saturation or suppression of the gluon density in the nucleus. A more differential measurement is here on the right, where you see the basic transverse momentum dependence of the JPSI production, this time in incoherent collisions. And you see the measurement here, which is, and the PT spectrum gives information on the spatial structure of the nucleus. And what you see is that it agrees, it's relatively flat. It agrees better with the green curve and this purple curve, which both have indicated that there's gluon hotspots inside the nucleus. So this, while the steeper model curves do not have these hotspots. So you see that the data give a clear indication of this let's say, fine structure within the nucleus. Now then going to the lead results. So one big field of study is the measurements of anisotropic flow. I'll be brief here because I assume that many of you are familiar with this. But what we do is we collide two nuclei, and then the interaction zone has this irregular shape, which you can characterize by azimuthal harmonics. And you see here drawn the second harmonic, which is the elliptic one, and then there's a third and a fourth harmonic. And we analyze those in the final state. So the expansion of the QGP gives rise to final state momentum and isotropy, which you see here on the right or in the middle. There's a picture of measurements of the V2 coefficient for different particle types as a function of transverse momentum. And one of the characteristic things that you see here is a clear mass dependence. So on the left, pions rise the fastest, then the kaons, they are a bit heavier, they go up at higher momentum, and then most of the baryons, which are even heavier, and also the fine meson, go up even later. And this is a clear sign that there is a collective expansion. So if you have a fluid that moves at a given velocity, particles with different mass get a different momentum. And that's what you see here at low transverse momentum. And then we, of course, also have measurements of the higher harmonics, V3 and V4. And I just flash here some examples. We have done that for many different particle types in the meantime. And then one of the things that we use is then to learn about the QGP is that we compare two models. And as I mentioned earlier, in a heavy ion collision, there are several phases. You have the initial state, then this expansion state, and hadronization. So I think the best way to do these comparisons is via this what they call Bayesian inference, where you run a model that has not only the, let's say, interesting physics, but also has some of the effects in it that you maybe don't want to study. And this is an example of such an analysis. This is already a few years old, but this has been, new versions of this have been done as well, where they compare their model calculation with the yields, the mean PT, and the flow coefficients as a function of centrality. And they run a very large set of models with different parameters. And then they compare to the data. And here at the bottom, you see which of these model curves are compatible with the data. And that way you basically fit the model parameters to the data. And what I like about this technique is that you fit also parameters of, for example, the initial state and so on. So you get really a comprehensive idea of the uncertainty in different areas. And one of the main results then of such a fit is the determination of the viscosity as a function of temperature, which here you see the shear viscosity as a function of temperature. You see that it's very low. It's about 0.1, which is the fundamental limit. And you see that it slowly increases as a function of temperature. And then at the bottom, you see the bulk viscosity as a function of temperature, which has a large uncertainty, but we also are starting to get a handle on that. And this very small viscosity means that there's a small mean free path, so strong interactions within the plasma. And here's a comparison of this result with other liquids, water and helium. And you see that the specific viscosity, the viscosity to entropy ratio in the QGP is actually very small, which means that it is a very ideal liquid. Okay, so these are results that we have been working on for many years, and I want to show you now a few more recent results in this area. So one is a recent measurement of the correlation between the event plane orientations, the psi2 and the psi3. And you see here the main result. The red points are the new Alice analysis, where this correlation is shown to be small, which is what I would have also naively expected, because the orientation of these, let's say, the triangular deformation within the interaction zone is more or less random. But there were previous results which actually showed a significant correlation, and the difference between the two analyses is a different treatment of numerical fluctuations of the number of particles in the collisions. And it turns out that this matters a lot. So not only the event plane orientation fluctuates, but also the V2 and V3 themselves. And here on the right, these results are then compared to model calculations, which show this expectation that there's not much correlation. Now you can also use these techniques to look for chiromagnetic effects, and there's a whole slew of studies on this, and one of the more recent ones is this analysis of what is called a chiromagnetic wave. The chiromagnetic wave is a difference between is a charge dependence of the V2, which is induced by this chiromagnetic effect. And what you see here is one of the plots from the paper is as a function of the charge asymmetry, so the yield, so the number of positive and negative particles compared. So here on the right you have more positive particles, on the left more negative particles. You see the V2 of positive and negative particles, and they have a very clear dependence. But their dependence turns out to be driven by background effects, which are related to charge conservation. And so further analysis was done to extract what we call the fraction of chiromagnetic wave effect, which is shown here. And you see that the current measurements are positive but small and are in line with no chiromagnetic wave effect. So there's an upper limit that about a quarter of the effect comes from the actual chiromagnetic wave. So now starting from this, after discussing a bit the soft sector, I would like to show a few results from a different type of measurement. So these are now what we call hard probes of the Quark-Gluon plasma. And to illustrate how that works, I'm showing here the PT spectra, the transverse momentum distributions of particles measured in proton-proton collisions and in lead-lead collisions, normalized by the number of binary collisions, so to compensate for the volume effect in lead-lead. And you see that the lead-lead results are below the proton-proton results, and that is due to energy loss, due to a shift that is actually a shift to the left on this plot. But we normally report this as the nuclear modification factor, which is actually the ratio of these spectra. And that you see here, so you see that this ratio is below 1, which means that there is energy loss at high PT. And at low PT, you see this bump, which comes from soft production, where the scaling is actually different. So when we discuss parton energy loss, we focus normally on the high PT, at least when we discuss the inclusive particle measurements, which are these. These are charged particle production as a function of transverse momentum. Now, a slightly more differential measurement that we can do is using heavy flavor. So this is now the summary of the open charm measurements of on the left, again, the nuclear modification factor. And the nice thing about charm is that the mass is much larger than the temperature of the Quark-Gluon plasma. So the production of charm happens all in the initial hard scatterings, and then they interact with the medium. So in this case, I should say that here again at high PT, you see the suppression, which is very similar actually to what we see for light flavors. But then at low PT, this enhancement is not due to number of participant scaling, but it's actually due to the fact that the yield that disappears at high PT due to energy loss, it all piles up at low PT. And then at very low PT, you're also sensitive to this gluon saturation effect that I mentioned before. And on the right, you see the elliptic flow measurements in the charm sector. So this again, this emphasizes what I just explained, that the physics at high and low PT is in a way slightly different. So you should really think here of energy loss, while here at low PT, it is charm conservation and the diffusion in the plasma that plays a role. And then for the V2, I think it's very interesting to realize that this initial production effect, that the initial production is azimuthally symmetric. So the full asymmetry that you get here must come from interactions with the Quark-Gluon plasma. And in fact, if you look at the numbers, the asymmetry in the charm sector is very similar to the light flavor sector. So it looks like charm really almost thermalizes in the medium in the Quark-Gluon plasma. So this is a slide explaining again the difference between light and heavy flavor. I think we don't need to go through that again. So let me just give you the upshot. So here again, there's a lot of physics going on, but what I wanted to highlight this study where they did something very similar to what I showed for the flow, a Bayesian analysis to extract the transport coefficient for high PT, the Q hat, and the diffusion coefficient, which governs the low PT processes, the D sub S. And the red bands are the results from a fit to the Alice data, looking both at the nuclear modification factor and the V2 that I just showed you. And you see that even for this heavy flavor sector, we are now constraining the transport coefficients as a function of temperature, both the spatial diffusion and the momentum diffusion coefficients. Now, more recently, we have been able to extend these kind of studies to beauty, and my kind of one-slide summary is this one. So we have done measurements in the hidden charm and beauty sector, so J psi and epsilon, and this is again the V2 as a function of PT. And you see that while for the J psi, there's a large azimuthal asymmetry, which comes from this diffusion effect, and then probably recombination of the CC bar pairs. You see that for beauty, the measurements, the red points, although the uncertainties are still large, are actually close to zero, which can mean two things, or has maybe two ingredients. One is that the beauty quark flow might be smaller than the charm quark flow. The other one is that in particular for this hidden beauty, the recombination might also not play such a strong role as it does for charm. That would also reduce the V2. And you see that some of the model calculations that we have are also indicating that we expect a small V2, but I think it's very interesting because for a long time, people did not expect charm to flow, and then we found that charm flows. But now we have a way to, in a way, turn off this effect by going to even larger mass to beauty. And there's something similar in the open sector. So the open charm V2 you see here in the red points, those are the points I showed before. But now we also have looked at open beauty by looking at non-prompt zeros. So they come from beauty decays. And you see that the flow is quite a bit smaller than for open charm. At this moment, I think the jury is still out whether that means that the beauty flow is not zero, but somewhere between light flavor and charm flow, or whether this effect comes mostly maybe from light quark flow. And I'm looking forward to model studies to understand this better, and maybe also a larger set of beauty flow studies, for example, using mesons and baryons separately to disentangle all of these effects. And that is really something that now upcoming with the new data from run 3, we should be able to make a lot of progress in. Now then, I already showed you a little bit of the J psi measurements. I just wanted to also show you this recent result where we measure the J psi RAA as a function of the PT, at forward rapidity, the blue points, and at mid rapidity, the red points. And again, there are two, let's say, regimes. One is at high transverse momentum, where we see a very large suppression, which in the case of charmonia probably comes more from dissociation, from the fact that a charmonium, a bound CC bar state, when it goes through the plasma, it is screened and it falls apart. And then at low PT, we see, compared to this suppression, we see an enhancement, or we see less suppression. And then what is which is interesting to see is that this enhancement is larger at mid rapidity than at forward rapidity, which is consistent with this idea that the charm and the anti-charm, they recombine. So you have at mid rapidity a larger charm density and therefore more recombination than at forward rapidity. Now coming back a little bit to the final state effects, I wanted to show you also this result. This is a measurement, a comprehensive measurement of the charm fragmentation. So where you see here on the left, the fragmentation to mesons. So these are just yields divided by the total charm yield. And then on the right, you see all the baryons and the J psi that we measured. And the big news here, which for charm has been known now for a while, is that the baryon production, which you see here in the lambda C, is much larger in PP collisions than it is in the plus or minus collisions, which are the points here, the lower points. And I like this plot because it shows really that we have done now a very comprehensive study For some of the other baryons, there's no information available from the plus and minus, so we can't really compare, but it looks like all the baryons are enhanced. And then here on the right, you see a recent update where we did the same analysis, but now for non-prompt lambda C and D, which come again from beauty. And also in the beauty sector, there's this large baryon enhancement. So what we see is that the baryon enhancement is there, so which might be a sign of recombination or of, for example, color reconnection effects. While on the other hand, the flow effects in the beauty sector are smaller than in the charm sector. Now then, I would like to come back a bit to this part on energy loss, where the last set of probes in that area are jets, and I just have a few highlights to show you from Alice. So jets are these very high energy clusters in a heavy ion event. So you see on the left a nice event display from Alice, where you see clearly high PT deposits sticking out, and this is from CMS, where you see a clear asymmetry between the leading and the subleading jet. So also jets, which can be very high energy, 200 GeV in this case, lose energy in the Quark-Gluon plasma. And again, we measure that with the RAA, with the nuclear modification factor, and this is a recent result from Alice, where you see the nuclear modification factor for jets with increasing jet radius, 0.2, 0.4, 0.6. And this measurement is made possible by doing a machine learning based subtraction of the charged particle background, because these very large jets, they have a very large contribution from background, which you need to carefully subtract. And that was for Alice for the first time possible with this technique. And you see that somewhat counterintuitively that the RAA decreases as you go to larger R, which is consistent with the idea that as the jets open up, you have more and more partons inside the jet, and each parton interacts and can lose energy. So in a way, the total cross-section or the total interaction with the medium is larger when you increase the jet size. Now, another area of jet studies is this, where we look at jet substructure, and there are many ways to do this. I only want to show one example here. This is a reconstruction of the jet, and then we look at how the jet axis changes when you use different algorithms. So, and one is the so-called soft drop, which is where you remove soft radiation from the jet, and then you look again at the jet direction. And the other one here is the so-called winner-takes-all axis, where you, instead of taking an average for the energy flow in the jet, you look at the highest momentum particles, and those determine your jet direction. And here you see these the angular difference between this winner-take-all axis and the standard axis compared in PP and lead-lead. And you see that in lead-lead, this peaks at smaller values, which it points to a hardening in the core of the jet, so that there are more hard fragments near the center of the jet. And that, again, by comparing two models, gives information about the coherence within the jet. And you see here that the red curve, with where all the partons are actually interacting independently with the medium, fits the data best. So that is consistent with what I just mentioned for these large jets losing more energy. And then finally, coming back to V2, to flow. So this is measurements of jet yields for in and out of plane. So you see here, this is the ratio of out of plane to in plane, and this ratio is below 1. So that shows that also jets flow, that there's more energy loss in the long direction than in the short direction. Now, in this analysis, something extra was done where we select events with a large Q2 and a small Q2. So meaning a large elliptic flow, events that are more asymmetric than the typical ones in the centrality range of 30 to 50% that we analyzed here. And the ones that have a smaller, that are more spherical. And you see that at low PT, the jets are even sensitive to these, let's say, shape fluctuations. So these are correlations between, let's say, low PT shape and the high PT probes of the chain. So now I would like to switch gears a little bit and show you a few examples of the using heavy ion collisions as a laboratory for hadronic interactions. And one of the techniques that we use here is the femtoscopy technique, which you probably know from using final state momentum correlations to measure the source size of or the shape of the nucleus by inverting this relation between the correlation function, the source function, and the interaction strength, which is the psi here, the two-particle wave function. But we can also invert this when we know the source distribution by measuring it, for example, with pion or proton pairs. We can determine the interaction potential, and that gives access to the interaction potentials of unstable hadrons or of rare particles like protons and pions, which you can't easily produce in the laboratory. And we have actually done a number of measurements like these, where you see proton lambda correlations, lambda kaon correlations, and even proton d-meson correlations. And these are, I mean, they all measure specific interaction potentials, and you see here a number of curves from different groups that predict these interaction potentials, and you see that our data are really constraining these models of the hadron interactions. And you see that for the light flavor, we have very high precision already, while for heavy flavor, we can do with a bit more statistics. And this is, again, one of the things we will get from the run 3 data. And the next step in this type of studies are 3-body interactions. So here we have proton-proton-proton correlations, where there is a significant difference at small q. There's only 1 point at the moment, but we have triggers that select these events in round 3. So we will study this in more detail, which is a sign of direct 3-body interactions. And also here for proton-deuteron correlations, we find that you can only describe them if you take into account the full 3-body interactions. But then for proton-proton-kaon correlations, there's actually no sign of 3-body of let's say direct 3-body interactions. So the 2-body interactions, they explain the full proton-proton-kaon effect. Now, another area of hadronic physics that we can do in ALICE is this. So these are on the left, the decay length distribution of lambda baryons. And you see here now the lifetime that we determine from our data. You see it's very high precision, very good statistics. And our measurement is about 3 times better than the previous world average. So this is very impressive precision in something that's not really heavy ion physics, but more hadronic physics. But I think a very cool measurement. And on the right, we have a similar measurement for a hypernucleus, for a hypertriton in this case, which is a proton, a neutron, and a lambda. And again, there our measurement is the most precise one to date. And it shows that the lifetime for this hypertriton is actually very close to the free lambda, which means that the binding is not affecting the decay width. Okay, so now I would like to slowly move towards our future plans. And to start it off, I want to come back to one thing that I skipped so far, is the thermal radiation. So we discussed a lot about the properties of the Quark-Gluon plasma, using, in fact, measurements that are also probing this hadronic phase. And one of the areas that is still, I would say, a bit open at the LHC is the measurement of thermal radiation from the initial stages and the QGP. So the thermal radiation really couples directly to these early phases and then escapes the interaction zone without interacting with it. And so far we have photon measurements, which are a good way to measure direct the thermal radiation. It's a very challenging measurement because there's a large background of decay photons from pi zeros and etas and so on. So after subtracting, this is what you find, and the systematic uncertainties are partially related to this subtraction. Now, even for direct photons, for photons that do not come from decays, there are 2 sources. One is hard scattering sources, which the calculation for those are given by these black lines. And you see they match well with the high PT part of the spectrum. And then there's the thermal radiation, which is dominant at lower PT, up to a few GeV. And you see here that our data indeed exceed the hard scattering expectation at low PT, and then there are several curves that give different expectations for thermal radiation. And experimentally, you can tease that out by subtracting these hard scattering contributions, and those are these spectra. So those are now as best as we can tell, the thermal radiation spectra. And what's nice to see is that they are quite smoothly exponential, what you expect from thermal radiation. But it's important to keep in mind that this measures a combination of the thermal emission, or let's say the temperature itself, and the radial expansion velocity. And one way to go beyond that is by looking at dilepton pairs, at low mass E plus E minus pairs. And just to give you a taste of how well, so we have first measurements in PP and in lead, but they don't show thermal radiation yet. But how well we can do that in round 3, I'm showing you this. This is the mass spectrum of E plus E minus pairs, and it has these backgrounds, let's say, or these signals of vector mesons and of the j psi and the epsilon. But it also has a contribution from heavy flavor decays, which can be rejected by DCA cuts. And that is illustrated here by looking at the distance of closest approach. So large DCA, you get the red spectrum, and those contain a large continuum contribution from heavy flavor pairs. And by taking only small DCAs, you get the blue points, which are then dominated by these resonance decays and by thermal radiation. Now, this is a measurement in PP, so there's not much thermal radiation, but this shows that we can really separate heavy flavor decays from the thermal radiation, and this analysis will be continued on PP and then also be done on the lead-lead collisions. So that is a nice introduction to briefly show you some of the upcoming upgrades. So as I mentioned, the analysis of round 3 data is still ahead of us. We're already planning some upgrades. So we are now in LHC round 3, and in 26, the long shutdown 3 will start. And in long shutdown 3, we will install the forward calorimeter upgrade and the ITS3 upgrade. ITS3 is a replacement of only the inner layers of the inner tracking system to provide even better pointing resolution, so to improve the plot that I just showed you. And then there will be round 4, another 4 years of running. And then in long shutdown 4, we are planning a large upgrade of ALICE, where we would like to replace the whole system, the whole detector, with a silicon-based high-precision tracker system that also covers then the forward rapidity up to rapidity 4. And that has also a number of particle identification systems at the time of flight and the ridge. I won't go in a lot of detail, but I want to give you a little bit of flavor of what we are doing. So for the forward calorimeter upgrade, which is a high granularity calorimeter to measure photon pairs and basically to reject these backgrounds of decay photons to measure again direct photons at forward rapidity, consisting of a hadronic calorimeter. Here you see a prototype, and an electromagnetic calorimeter with the other prototype. So this electromagnetic calorimeter is really a high-tech device with tungsten and silicon. So the tungsten is the conversion layers, and then silicon sensors to, with a very high granularity, measure the particles or the showers of the photons. And you see here that this is a simulation, but you see that with this device using the pixel layers, there are 2 pixel layers with a very high granularity. One can actually distinguish photons at a few millimeter distance from each other. And so these prototypes have been tested with beam, and here you see, as an example, you see the energy resolution as a function of energy, which is well within the specifications that we require, and the technical design report has just been submitted to the LHCC. Now for the ITS3, I just wanted to show a little bit more broadly that we are working actually on a family of developments for pixel sensors. So we already installed this pixel-based, CMOS monolithic pixel-based tracker, which uses this type of device where you have the sensor and the electronics in one CMOS sensor, and the CMOS means that it is it's an industry standard production process, so it's relatively affordable for these large areas. And we are now developing this further with a new generation, a new technology, using again this CMOS, but with a finer pitch, a higher resolution. And first tests have been done with and have been already published with this in this paper using the 65 nanometer technology. And that is the main ingredient for this ITS3 upgrade, where we then go to very thin layers of silicon. If you thin silicon enough, it becomes flexible, and you can make curved layers that kind of support themselves around the interaction point. So it allows to go very close to the interaction point and to make very thin sensor layers. And that technology we also want to exploit then for LS3, where we then want to go even closer to the interaction point. So one of the highlights of the LS3 upgrade is this retractable vertex tracker, which can open when we inject the beams. We have a larger radius of the inner tracker, and then when we turn these petals around, they form a tracker with a very small opening, and the first tracking layer is at about 5 millimeters from the interaction point. And this, on the left, it shows you the evolution of the performance in terms of, let's say, statistics, acceptance times interaction rate, and then pointing resolution, where you see that every time we upgrade, we make a step in one or both of these parameters. And LS3 will be a step both in the acceptance and the interaction rate and in the pointing resolution. So I just wanted to, I'm wrapping up, but I just wanted to show you two highlights of the physics program for LS3. So here you see the dilepton measurement projection for run 3. So this is the precision of let's say, the thermal part of the spectrum that we can measure with in the upcoming runs. And then on the middle, you see the same measurement from LS3, again, a projection. And you see that in the thermal range, we can reach even higher precision, which allows us to do differential measurements and to pick apart the time dependence of the emission spectrum, and also to look at this rho A1 mixing, which is related to chiral symmetry restoration. So for that, you need really good precision, because the effect of the rho A1 mixing is really small in this, just around the resonance region. And here on the right, you see then one example of a more differential measurement. So this is the V2 of the thermal dielectrons. Again, a projection for the LS3 statistics and precision. Now, another set of measurements that we can do with LS3 are measurements of CC bar correlations. And the idea there is these are produced back to back. And when they move through the plasma, they get kicks, and the back-to-back nature is disturbed, and they get a transverse motion, which here on the left you see a theory calculation that shows that in particular at very low PT, there's a very large effect of these thermal kicks on the correlation. And this shows a projection of how well we can measure that with LS3. And here is a projection that we made for run 3 and 4. So you see that really this improved pointing resolution is instrumental to be able to do these kind of differential measurements of the interactions of the charm quarks with the plasma. Now, and for LS3, the R&D is starting up, and I just show you here kind of an overview of recent studies. So we're working on this inner tracking, this vertex tracker that I mentioned before, using both on the sensor technology and the mechanics of these petals. But in parallel, also groups are working on the timing sensor developments for a time of flight measurement, using actually different technologies. This is what I would call more standard LGAT technology, but we are pushing really the time resolution by using thinner sensors. And there's also work going on to make integrated sensors, so to have the CMOS sensors for time with a high time resolution. And then for the ring imaging Cherenkov, we are looking into photon sensors, and again, see whether we can make integrated circuits that have both the sensing and the electronics in one chip for the photon measurement. And then there are other areas. So there's a muon detector and there's an electromagnetic calorimeter being proposed, for which also R&D and test beams are ongoing. So I think this is a very interesting area where now is the time to get involved in the studies so that you have an impact on how LS3 will be shaped. So with that, I would conclude. So I showed you a brief but compact overview of what we have been doing in ALICE. And so we study the condensed matter of the strong interaction at high temperature. And I've shown you several examples of how we measure the interaction properties, the viscosity and the high PT interaction properties. And they all indicate that there's a short mean free path and strong residual interactions. And now with the upgrades that we've just performed, we'll be able to go to much higher precision for heavy quark measurements and the first measurements of the thermal radiation with dileptons. And I've shown you that we also use the collisions as a laboratory for hadron physics. And at the same time, in parallel, we're working on R&D for silicon sensor technology in many areas for LS3. So thank you for your attention. And, thank you. Sorry for being a bit long, but
no, it's perfect. So first, we sincerely appreciate Marco first come to Shanghai and stop by our university and also give this excellent talk, a very comprehensive overview. So I believe both junior student and senior scientists can learn something. So let's see if we have any question. Starting from our on-site audience. So feel free to raise your hand and yes.
Thank you very much for the talk with lots of interesting results. Can you go to the slide on the GIPSA IA? So I want to see, because you compare the central accretion. This one. Because you compare the central accretion at mid rapidity to the mid central at forward rapidity. The blue is the forward rapidity, right?
Yes, yeah.
So I wonder if you also have the measurement at mid rapidity for the mid central accretion, the data.
Yes, it's not really. It's a very good question, but the difference is really 0 to 10 and 0 to 20.
Both are central.
Both are central. So it is unfortunate that we don't have 0 to 10 for both. I think it has to do with we took an online trigger data sample for this for the central barrel detector. So we have only 0 to 10 from the 2018 data, and we should. And I think for some reason we did not take the 0 to 10 with the muons, but I think it would look very similar.
Also, if you have a differential centrality measurement at the
okay, so this you really want to know about mid-central? Yes, in the paper it's there. So I don't have it here, but we.
Yeah, I want to see.
And then you see less of this enhancement at 30 to 50%.
Okay.
Yeah.
Okay.
Yeah.
And also, I want to see if you have a result on the beauty side. These similar dependence.
Not yet. Not yet. Yeah. That would be very interesting if you. But it's more. You need more data for it. And I think if you look, is it shown here? No. So we have a plot of the PP plus minus spectrum where you actually see the epsilon peaks now in round 3, but we haven't determined the use yet.
Yes, because we have a college here actually working on the S-Physics.
Yeah.
Yeah, and just data is here, and he's working on the epsilon.
Yeah. So I think we have some results for the forward rapidity in the muon arm, but we with the new data. I think we should be able to do it also at mid rapidity in the plus and minus channel.
Thank you.
Hi, very nice talk. I have two small questions. One is, do you have measurements for active correlation to dynamic diagonal?
Sure.
HDT measurements for dynamic or diagonal?
Di lambda or di omega HPT. I am not sure. Maybe di lambda, we do have di omega, not yet. Lambda, I think yes. Yeah. But and we have also, let's say, proton omega, for example, which is also showing these interaction potentials. Because then for the di lambda, the question is whether there's a dibaryon or lambda bar, lambda, whether there's a dibaryon. So we haven't seen a dibaryon. We have analyzed the interaction potentials to see whether there's room for a bound state. If I remember correctly, it was a bit ambiguous. So there was probably not, but it was just on the edge.
Another question is about the thermal radiation gas. So how to isolate the thermal radiation from other contributions?
So that's why I kind of emphasize the dileptons, because in the dileptons it is relatively pure. So what you do also you have of course combinatorial background coming from these resonances, and also that you have zero PT or zero mass as the pi zero, the Dalis decay of the pi zero. But you do always this subtraction of like sign pairs, which gets rid of a lot of the combinatorial background from these sources. And that means that here in this mass range between the phi and the j psi, you have a relatively pure signal, thermal and heavy flavor, and then by doing these DCA cuts and maybe varying them, you can measure the heavy flavor separately from the thermal radiation.
So this diagram is for PP?
Yeah, this is for PP because this is where we have now, let's say, recent high statistics, but we have, and what we would like to do is to look at high multiplicity PP to see whether we see thermal radiation. But of course, it is more of a reference measurement at the moment.
You can also check whether the low exception of zero nano into low markers in high
Yeah.
See whether any chance in zone.
Yeah, that's a good idea. Yeah. So we have already published results from PP, but I'm not sure. So there's no sign of thermal radiation, of course. There was, although there is a small excess at very low PT, but I hope that now with run 3 we get a much better precision and we can go to very high multiplicity and look specifically there.
Thank you. The tests are really silicon tracking to with this. What's the benefit?
So you're asking what is the benefit of having silicon tracker instead of a TPC? So the main benefit is the fact that you can run at higher rates. So you can, because the TPC with the phase charge built up, 50 kilohertz is probably the limit of what you can do. And then also you can of course have a faster readout with the silicon. Also, but this is more practical advantage is that so this design is a compact design. So you have a high field, 1 to 2 Tesla, and the radius is only 1 meter. Well, the current Alice has a radius of 3 or 4 meters. So the outer radius of the TPC is 3 meters, and then there's still more detectors outside with half a Tesla. But this is almost an even trade-off. By going more compact and to a higher field, you get similar, let's say, momentum resolution than you have with the larger lever arm and the lower field.
Like gluon and more fully
that's a good question. So the silicon sensors refers to all the inner parts, but the muon chambers will probably be different technology. So there's an absorber, and then outside there will be either scintillator detectors or RPCs for the muon detection on the outside. You don't need very high granularity there. So that's
another junior students. You really don't have much opportunity to talk to Mrs. Spokesperson directly. So believe me, seize the chance. Feel free to ask anything, or even a very general one. It doesn't matter.
Don't be shy.
Okay, yeah. So this is a very important thing to do experiment. Any question from our online audience? You can just leave message in the chat box or raise your hand. Let us know, or just feel free to unmute and speak out. Okay, I don't see any. So yeah, probably many Alice people online will meet in person this week. So
yeah,
probably don't bother to ask.
Okay, thanks everyone.
Or is there anything else? Not only question, I mean, relate to the seminar, also any other now you want to discuss. Okay, so if no more, we thank Marco again, and we thanks to everyone for joining us online. So we close the seminar. Thank you.
Thank you.